Okay, good morning. In the last several classes we talked about organolithium compounds. So, if you think about the periodic table, now we have to move to little heavier atoms, and next atom is magnesium. So, in today's class we will exclusively talk about magnesium and zinc. Okay. We will give you a rough idea about the position of magnesium and zinc in heterocyclic chemistry, but you can think of a greater use of both magnesium and zinc in near future, simply because there are many more new methods are coming up, and methods for preparation of organomagnesium and organozinc compounds. And to begin with, I will just introduce you to a very active kind of metal, and which is known as Reiki zinc or Reiki zinc. Reiki metals. If you go to the Wikipedia, they will say Reiki metals, but for us magnesium and zinc should be all right. Magnesium should be Reiki is basically an organic chemist, and he is in the University of Nebraska, Lincoln, USA. So, he still is a professor, but and he has opened up an also an industry how to make reactive metals. For example, magnesium is not known to react with a double bond, carbon-carbon double bond, but if you have a very highly reactive magnesium, it can react, provided that is a conjugated one. For example, it can react with butadiene to form cyclic magnesium compounds, magnesium intermediates. Okay. What is the specialty? Specialty is nothing, very simple, that you take a magnesium salt and then reduce it with a metal, reducing the metal, unlike electrochemical preparation. And in this case, if you use let us say potassium, so all of us can guess what would be, and then this chloride, and in the place of potassium also one can use lithium or sodium. So, probably it is the tricks lie in the preparation of the or the use or the conditions whatever, but the net result is that you get this active magnesium. Okay. So, this active magnesium is used for the preparation of organomagnesium compounds. So, all of us know the typical organometallic preparations requires fundamentally three different methods, right. One is, the very first one is how to make an organometallic compound. How to make an organometallic compound. The first thing that which comes to our mind is deprotonation. That means you remove a proton. So, by which one can produce a magnesium, organomagnesium. For example, all of us know, right, if you have acetylene, and if you react with ethyl magnesium iodide or so all of us know what is the product, again a new organomagnesium compound, new organomagnesium compound. So, this is then next important thing is could be halogen exchange. So, it is an exchange with halogen, we will talk about examples today. So, we begin with an okay. But the combination has to be right combinations, means the organomagnesium that will be produced should be weaker nucleophile, weaker base, okay, because these are the basic conditions. All these organometallics actually are referred to as base or bases. Okay. So, that means the reaction would proceed in the forward direction, provided like in this example, in the previous example, for example, on your left hand side you had a ethyl magnesium iodide, and on the right hand side is. Now, if you compare this ethyl minus and acetylene minus, which one is more stable, all of us know the stability goes to acetylene or less basic, less nucleophilic. So, this is the pattern. So, in the halogen exchange also would follow the similar pattern, and the third option that is applies in this particular example. What is the third option? All of us know by now. Know what is the third option of preparing an organometallic compounds? Very good. Because lithium case it was not there, because that is the lowest, the lightest metal. but in this case you can use the transmetallation. So, transmetallation, that means for transmetallation in the case of magnesium, only option you have is the lithium. So, if you have a organolithium compound and then use let us say magnesium bromide. So, what you are likely to get this and lithium bromide. So, like this you can go on, and if you want to let us say make a zinc compound, I mean you can take organolithium or organomagnesium and then add. That means transmetallation normally goes in favor of the heavier atoms, heavier and less electronegative, electropositive atoms. Okay, that is the trend. And now coming to this heterocyclic chemistry, I think very first thing that we should talk about the case of, let us say for example pyrrole. Now let us look at the feasibility of these reactions, methyl magnesium iodide, which is commonly made. So what kind of reactions do we expect out here? Normally methyl magnesium iodide is nucleophilic in nature, but very first thing you should consider is the deprotonation reactions or the halogen exchange reactions. Those are the first reactions. Now we have an active proton here, whether we should think about it. That means is it a possibility instead of the hydrogen, if you have magnesium iodide, the other thing is methane. So is it a possibility? How do I know whether it is feasible? Basically you have to think about this acidity, NH acidity. Between NH acidity and methane acidity, which one is, all of us know which one is more acidic. Pyrrole hydrogen is more acidic. So the corresponding magnesium compound would be resulting from these reactions. That is perfectly all right. Then this problem. Now if you want to do a reaction, for example, let us say Rx. So Rx, so there are actually several options. How many options? Three. There are clearly three different options. 2, 3, 1, 1, 2, 3, all. That means nitrogen can be alkylated, C2 can be alkylated, C3 can be alkylated, and in fact, and this is not a very good reactions for the pyrrole chemistry. If you think about these organomagnesiums, okay, I mean all the three different reactions are reaction products are known in the literature. Okay, now go to that means it is not very encouraging. Well, there are people have tried to optimize the reaction conditions by changing the solvent, this thing, that thing, but eventually, the reaction is not a very clear cut reactions for. Okay, then obviously what is our next option? Next option is indole. So after pyrrole, the next option could be indole, and as usual. So if you take let us say ethyl, in this case ethyl often is used because ethyl is preferred to methyl in generating organomagnesium compounds, simply because it heavy, little higher boiling, that is it, and so easier to handle methyl bromide. And so now what you will see that one of the options is now reduced. So you have now pyrrole magnesium bromide, indole magnesium bromide. So and all of us know, due to the resonance, these indole reactions takes place at the C3 position, C3 position, and there is also a possibility that the reactions and also can take place. That means there are two possibilities. Okay, say alkylation, I can say, we write. See, there are C alkylations, acylations, all these possibilities are there, and similarly N alkylation and N acylations, all these reactions are possible, all these reactions are possible. Okay, just giving you one example. If you react this magnesium compound with a ribose sugar, I will not indicate the stereochemistry to make it simpler. So if you write this benzyl protected ribose sugar and this, so you are likely to get two different products, likely to get two different products, or other you can say 4 different products, all kinds of products. But in this particular example, there are 2 different products have been found. One of them is N-alkylated product, and the product again a ribose compound, then benzyl and CH2 benzyl. The other possible product is now C-alkylated product or C product. So, hydrogen and benzyl is an open chain compound, so it should be OH, then benzyl, and this one is OH. Now, I think we can explain very simply, because this is nothing but, if you rewrite, this is nothing but it is an OH up here, and this is nothing, and this is basically an aldehyde, right. All of us know that sugar is an aldehyde, and in equilibrium they exist as aldehydes. So, basically that means the starting material itself has dual reactivity, and after the reaction is over, so you can get the cyclic and acyclic compound, that all of us know. Then in addition, there is a possibility that N-alkylation takes place, or the C-alkylation or C-acylation takes place. All these possible. In this particular example, that these 2 compounds have been identified, but the striking thing is that both are produced, but in unequal amounts. This first one is produced in 86%, 6 to 14 ratio, and the solvent used was THF. By choosing this example, just I would like to say that these organometallic reactions are very sensitive to reaction conditions, temperature as well as the solvent. Now, if the same reaction if carried out in DCM, dichloromethane, and you see here you get exclusively C product, okay, C product. So, that is basically that is the point. That means, if you are handling with an organomagnesium compound, there is a reactions possible with ambient nucleophile. So, the ratio of the products can be changed probably by changing the reaction conditions. Now, look at a similar reaction, but little different. Again you take indole magnesium bromide, and in this case the reactant is imide, succinamide, and then it is substituted with 2 chlorine atoms. Okay. So, nothing, just basically they are mixed together. So, what do you expect? Now we have to look for. So, this is highly acidic, this nitrogen is highly acidic because it is such imide. So, it can destroy as part of it, okay, even there is part of it. Then what else possible? Then the amide carbonyls are not very reactive towards Grignard, all of us know, okay. So, that is the difference between organolithium and organomagnesium. So, one of these reactions is basically indicative of the relative reactivity. We will come to that later when we talk about organolithium and other metal compounds. What are the marked difference between the 2 classes? Organolithium, that means organolithium has a specialty that they are very reactive. At the same time, you can control their reactivity. Okay, that is the advantage with organolithium compounds. And like you can do the transmetallation, you can reduce the reactivity. You can reduce the temperature, you can moderate the reactivity, all these possibilities. So, in any case, in this case, already by virtue of having the metal magnesium, it itself is quite less reactive. So, and that means nucleophilic addition is not taking place, or that means it is an addition and elimination reaction takes place at the site of the chlorine, eventual result is a molecule you can so this is so of course it will require twice of these magnesium reagent, and this is hydrogen, this is hydrogen, this is hydrogen. Many of you will be wondering why such a reaction was taken up. I mean, there are all possible reactions with organomagnesium. Actually, if you oxidize, you get these, you get 1, 2, 3, 4, 5, 6. You get basically a carbazole kind of molecule, and the molecule eventually is elaborated to a molecule known as staurosporinone. Staurosporinone is an advanced intermediate for a very natural products. Okay, but we don't worry about this. It's a little more complicated than this, and so now let us that means let us say what next. Again, we restrict our examples to organomagnesium and 5-membered ring. For example, if you are to make a benzothiazole, organomagnesium compound, something like this X. So, what reagent would you choose? What reagent would you choose? That is important. And you know, there are other, what procedure would you adopt? I have already said that these for generation of organomagnesium, deprotonations, halogen exchange, and the transmetallations. So, we have already seen that these 5-membered heterocycles with active hydrogen can be deprotonated with lithium reagents. So, you can do the transmetallation. Okay. But in this particular example, you do not have to. Why should you incorporate lithium, which is quite more expensive than magnesium? So, if you directly can convert this, that is perfectly all right. So, how do I directly do this? What are the reagents available? Okay. So far we have seen methyl magnesium bromide, but typically actually typically in this example tertiary butyl magnesium bromide could be used, ethyl magnesium chloride could be used, or ethyl magnesium bromide could be used, and there are many instances where you can use also, this is very popular reagent, isopropyl magnesium chloride. Reason being, this is readily available. Isopropyl chloride is cheaper than many other halogenating agent, and so one of these things would do. Okay. Then once you have this, you can go to these rest of the typical reactions of the organomagnesium compound. This particular compound was made in a scale of 10 kg. Do you understand the meaning? Reason being, it is actually it is used as a reactive reagent in a pharmaceutical industry. If you are interested, I can give you the reference. This was published in 2007, JOC and 9798 page number. By giving what I mean to say, the meaning Grignard can be done in kgs. I have seen a reaction called Birch reduction. I do not know whether you know or not. Birch reduction is done in liquid ammonia by adding lithium or sodium. Lithium is less violent, but as you go to sodium, it becomes more violent. But they just dump kgs and kgs of sodium, without taking that is in Madras. There is a chemical company called Orchid Chemicals. Colony, do you know? Orchid Chemicals. No, Madras, Chennai. If you walk in the city Madras, their tower is so big you can see from distance. Okay. Any case, so this was reacted with a compound. Okay, I'll just in short will write, and then you have to predict what could be the product. Okay. Apparently it looks like an amino acid derivative, and it is a 5-membered nucleus, I think by all of us know what it is, then NH Boc, and amino acid means this is a well defined stereochemistry, and then here then you have one more moiety NH, and I think I write Pg to abbreviate. Pg is protecting group and NH. Okay. So, this is the other reactant. Okay. I think by have you recognized what is the other heterocyclic moiety? Imidazole. Fine, good. So, I mean actually after a semester you will forget. So, that is why I am asking this. Okay. And this part is known as guanidine. So, that means there is a center of amino acid, there is a center of this thing, and this is guanidine, and you have a now heterocyclic Grignard reagent. So, you have to predict the reaction product. So, what is the product do you expect? Okay. So, where do you start from? Organometallics, they go for abstraction of protons, the addition and displacement, all these things. Okay. There is a possibility normally, I mean unless the conditions are mentioned, you will not be able to predict whether this NH is sufficiently acidic or not. Guanidine nitrogen is not very acidic, all of us know guanidine is a base. So, it is likely to be not to be very highly active. So, what are the other active hydrogen? NH Boc hydrogen could be acidic, sufficiently acidic, because imide hydrogen. And other possibility if the reactions are prolonged, like in the previous example if you recall, the sugar OH was free. So, if you have excess of Grignard, Grignard would consume the OH hydrogen and then rings opens up, becomes aldehyde, then reaction takes place. So, likewise the reaction there is a possibility. And what is the possible reaction? The possible reactions, one of the possible reactions now is one of the possible reactions could be this benzothiazole, this nitrogen, and this amino acid part NH and Boc, and rest of the things here. So, this is a possibility. Now, first of all you have to identify whether this is a possibility or not. How do you know? How do I know? So, that means if this is the reaction possible, then that the group that should come out is this one, imidazole. Now, is it a possibility? How do I know? That same old thing, that it should produce a weaker base, and is it a weaker base or not? That is what I have to know. Now, you have enough of heterocyclic chemistry or knowledge. So, in the previous case it was also a 5-membered heterocycle with 2 atoms, right, and in this case also 5-membered heterocycle with 2 atoms. But mind it, the acid corresponding to the benzothiazole is a CH, sp2CH hydrogen, and in this case you have NH hydrogen, and that too again a pyrrolic hydrogen. So, all of us know pyrrolic hydrogens are more acidic than any other, I mean the corresponding, okay, and because pyrrole forms salt with potassium metals, etc., etc. So, it is such a nice, even potassium hydroxide is sufficient to abstract the proton from pyrrole NH. So, these are the things you have to remember. Okay. So, that means this reaction is quite feasible one. Now, just we will take up one more very important nucleus. I don't know again this nucleus is produced in kgs and tons, and this is basically a starting material for polythiophene. Have you heard of it? Oligothiophene. Have you heard? What are they famous for? Louder. Conductor, I should say, not semicon. Well, if you dope it, becomes conductor, fine. Yes, very useful, Oligothiophenes and polythiophene. They are very useful for conducting material. It can be made use for preparing, organic transistors, okay, and then thin films, conducting thin films, all these things, and they are produced. These polythiophene or oligothiophene are produced in tons, again in tons. That is what one of my students said who worked on this. Okay, in this case, what you see, there is a hexyl moiety. Axial moiety is basically is required for make it a processable, means solubility problem is removed. Now, if we are to make a Grignard, in this case the Grignard has been that has been used is TMP and magnesium chloride and lithium chloride. TMP, magnesium chloride, lithium chloride. I think do you know what it is? Actually, it is a tetramethyl piperidite. Tetramethyl piperidite, and this is magnesium chloride and lithium chloride. It is a very popular base. It is a very hindered base, reactive base, sufficiently reactive, as you will see in a minute. It is a very reactive base, and this is recently been known as Paul Nockel, is a German scientist. Paul Nockel. So actually it is known as Nockel and Hauser, and this Hauser is C.R. Hauser, Charles Ridge Hauser, something like that. It is a pretty old person. So it is now known as Nockel Hauser base. In the previous class we learned a new base called Fort base, and now this is okay. So these are all the compositions are different, but this is found to be pretty useful. And if you use this base, and this Professor Nockel, and I think he's I think junior to me by maybe by 2-3 years, and he was in US for some time. Then he moved to Germany, and throughout his life he is working on this zinc and magnesium. So you see there is so much to do, this field, okay. And he has popularized organomagnesiums in different fields, and he also recently he has used synthesized ellipticin, a natural product. And so once you do this, what you will find, there are striking behaviors of these reagents. One of them is the deprotonation. You can directly deprotonate and produce this magnesium reagent, that is Grignard. And you have to note here, it gives only selectively one hydrogen, okay. And all of us know the hydrogen adjacent to the heteroatom is more acidic in nature, and so one of these two hydrogen, but also one can just quickly guess, because of the tetramethyl piperidal steric bulk, it is not approaching the 2 positions. So it is approaching the 5 position. So it can be, the steric bulk also can be made use of in doing a selective deprotonations or magnesiations. That is it. So once you have these, then you can you do all kinds of things. For example, you have this, all of us know, but you see, you have to note, few minutes ago I said that these organomagnesiums are not very reactive towards amide, but again now I am telling you that, okay, but why? So in this case DMF is nothing but is a formulating agent. So in this case it is reacting. So there are some of these tricky reactivities you have to take note of, that is it, because it is a 5-membered heterocycle. So it is a pi excessive. So it is likely to be more nucleophilic than simple aromatics, okay. And now let us say, what is how to make this oligo. So if you take now one more thiophene, I think then you just couple them, that is what we call coupling, right. So in the next class actually we will be talking, just summarize, because some of you know all these couplings, but just summarize what the couplings are. And so cross couplings. So you have two different heterocyclic moiety, you just couple them, but in this case it is magnesium. So you have to also remember some of the things, that which particular conditions are required for the magnesium coupling. One of the coupling last class I talked about, right, Kumada coupling. Kumada coupling requires iron, but also this is basically any kind of coupling with magnesium reagent, organomagnesium reagents are known as the Kumada coupling, okay. And in this case the reagent that is used is nickel chloride and PPP, I think by now all of us know, 4th year I taught, right. Any research scholar who knows what DPPP? Maybe diphenyl, that means diphenyl phosphenopropan, that is it. Okay. So, what is the result? The result is hex, and of course, then this. Then that means you get an advanced monomer, and then that can be polymerized. Okay. So, what else? One or two more maybe. I think I will just skip some of the examples. They are typically the extension of what we have talked about. Now, let us this is an example which gives you a lot of lessons actually. Lessons here. The starting is thiophene again. If you recall, in the previous case, the thiophene magnesium chloride was made by deprotonation. In this case, you take isopropyl magnesium bromide. There is a possibility of deprotonations because you have a hydrogen up here, and all these things. Fine. And so many things can happen. It can take deprotonation, it can do deprotonation, it can do the halogen exchange. Okay, it can do halogen exchange, it can attack the ester, because in this from the school we have been learning that organomagnesium means it will react with an ester to form the corresponding ketone or alcohols, right. But just by proper choice of organomagnesium, in this case it is a little bulkier. So, you are rather directing the group to either to protonations or halogen exchange. Protonations and deprotonations and halogen exchange often compete with each other in terms of the rates. So, now and I mean you can guess which one is likely to be removed. Okay, since this hydrogen is away from sulfur, is not, so that is not very favorable one. So, between the two bromine then, and the steric bulk has prevented its reactions with the ester group. So, then halogen exchange. Now, which halogen? Just a guess, because it forms a sort of a carbon ion. So, it is for a carbon ion. So, you have an electron withdrawing groups here, the ester. So, it is likely that this is being removed, and you get the transmetals. Fine. Now, you want to let us say elaborate this one to corresponding allyl substituted compounds. So, what would be your choice? If we did not know anything, we would have done just quenched with allyl bromide, but that gives a lot of complications. I told you once before, the organomagnesiums are good, but in certain cases they are very complicated. I mean direct, that is the reason, that is the genesis of Kumada coupling. Why Kumada coupling was required? Because straight reactions of the organogrignards with the alkylating agents are not very straightforward. Okay, because of many problems. One of these problems is again a transmetal. This is a grignard, this is an halide, again a not transmetal, so halogen exchange can take place. Depending on their marginal pK differences. Okay. So what should be the next step then? We want to get to this one. So what should we do? We moderate the reactivity, or moderate the reactivity or change the reactivity. So how to moderate the reactivity? Go to the transmetallations. So the commonest reagent for the transmetallations, okay, because normally, okay, when you go to think about transmetallations, you should first think about non-transition metals, but in the, if you have magnesium, then of course there is no other, but you have to go to the transition metals. Then once you go to there, then you have to find the one which is somewhat cheaper, okay. And the cuprous cyanide is cheaper, and there are 2 lithium chloride. This lithium chloride actually provides the solubility to this cuprous cyanide. So this reagent should be soluble in partly in organic solvents. So once you have this, then so you have now cuprous cyanide, and eventually you will get these copper reagents, okay, organocoppers. And now the reaction smoothly proceeds to get to these compounds. So this is a nice example actually. It gives you a different way of making this and that and this. So likewise, exactly same. For example, you want to apply this sequence to indole chemistry. You take in a protected indole and diiodoindole. So you apply the same sequence as above. So what do you expect? Now you have an option selectivity. So you have 2 different iodines, and obviously now you know which one, the one next to the nitrogen, and you will get to the product. So that means one iodine can be selectively okay. And so let us take just 1 or 2 more maybe examples from the 6 member ring systems. This is something which I could not explain, probably you would be able to explain. That means there are some results which cannot be explained. Once again, isopropyl chloride. So isopropyl magnesium chloride. So what would you expect? What would you expect from this reaction? Well, one thing I can say that, okay, unlike butyl lithium, remember Chichi-Babin reactions. There is a possibility of Chichi-Babin reactions, but again butyl lithium, phenyl lithium, they are more nucleophilic than the corresponding Grignard. So we cannot expect a Chichi-Babin kind of reactions here, right? So then obvious is halogen exchange possibility, there is a possibility. Now which halogen? That's what I thought. That's what some maybe we have to invoke something else, but in this case the reaction has taken place on the other halogen. I don't know whether you can then if you do this, all these reactions are same. Now if you react with acetaldehyde, so a new CC bond will be formed, CC bond, that is typical of the Grignard reactions. So you will have this, okay. And one more example probably, again a pyridine case. Now you have iodine and chlorine. So if you use this previous reagent, so what do you expect? Now this is a little complicated. In the previous case both were bromine, but in this case one is iodine, one is bromine. So that means a bond strength as well as this acidity, etc. But like before, that means the iodine is removed and you get the corresponding magnesium chloride, this magnesium chloride, okay, magnesium chloride. Maybe we will take one more fused system. This is an example where you have iodine and nitro. This is a special example. Maybe if the time permits, we will talk about a little bit of these things, the organomagnesium compounds towards the nitro compounds, and in this case this example requires phenyl magnesium chloride. There is a special kind of reactions we will be talking about probably towards the end of the class, maybe, or in the next class. What you can see, there are once again so many possibilities, nucleophilic addition to these 2 positions here. Okay. Then addition elimination can take place. You have iodo compounds, right? Iodo compounds, in case of pyrrole we have seen, if you have chlorine undergoes addition elimination and then essentially displacing the sp2 halogens. So, there is a possibility, and also you have to take note of the other possibilities. The other possibilities is this halogen exchange. So, halogen exchange between the addition elimination and halogen exchange also is a possibility. It depends on the reactivity of the organogrignard. If the grignard is pretty reactive, then it is likely to that you can get this halogen exchange done. Okay. This could be then I have a special reactions only for the saturated heterocycle. This could be useful for Ovisec. It is an aziridine case. Aziridine case you have now is a sulfoxide and a phenyl aziridine. Now, if you use ethyl magnesium bromide, let us see. What could be the possibility? What reactions do we expect? Aziridine opening, right? Why should it open? Even before using this reagent, that was also strength. So, in coming contact with this strength does not increase, right. Fundamentally, if you see, organic reactions are not many: addition, substitution, eliminations, and these things, those few organic reactions. Okay. So, why not first addition? So, actually in this example, this is a peculiar example here. It attacks the sulfoxide, it forms a magnesium reagent here, magnesium bromide. By showing the bonds here, I mean to say the stereochemistry is retained. So, bromide and this is magnesium. So, this is actually also this is nice way of making the corresponding carbon ion. That means, sulfoxide can be used as a carbon ion source. Okay. And so far we have talked very quickly. I will just give you these. This is a very important guideline, by the way. So, there are bonds in organometallics normally are classified, in several kinds, and then percentage ionic character, for example. So, in organometallic chemistry, so we talked about, let us say, lithium, organolithium. Okay, percentage ionic character of organolithium could be how much? Any idea? Oh, really? How did you know? That is interesting. Huh? We remember it. That is great. Exactly 43. That is real great. Okay. Then you have to tell me this one. Then I will. I think I will. Okay. What about potassium? Well, in my note it is 51. Okay. And then the other extreme, copper. Huh? Copper is 9. So, now you can fill in the blanks, right? Now you can fill in the blanks. This gives you some idea. What does it tell you? If you have an organopotassium, that becomes more. I would write. I would say basicity. How is that? Basicity goes up in this direction. All of us know basicity has some resemblance with the nucleophilicity. So, if you have a potassium salt, that becomes more nucleophilic. So, similarly, then where should magnesium fit in? Magnesium on the top or below? Okay, good. So, how much is it? 35. That is interesting. This is or pure gambling or what? It is good. 35. Yes, very right. That is great. Okay. So, like this, you can rank them. Well, but for us the numbers are not that important. Numbers are the to us the importance is the order. So, if anybody has come across a base called Schlosser's base, what is it? Moon? You nodded your head. What is it? And then the fourth year we talked about Schlosser's base. Schlosser's base is butyl lithium and potassium tertiary butoxide. What does it do? It just exchange the metals. So, it becomes carbon potassium bond. So, it becomes more nucleophilic, more basic, one of the strongest base used in organic chemistry. Okay. So, that means this order is a very useful one. Then okay, where do you put then organozinc, because today's topic was organozinc. Here below magnesium. So, that means below magnesium. Now, Supriti, tell me what is the value? Close 18. So, you see there is a dramatic difference between organomagnesium and organozinc. What does it tell you? Organozinc is less reactive than. So, that is why they do not react with organozincs do not react with esters, and that is the origin of Reformatsky reactions. But if you want to sp2 halogen sp2 zinc, how do you produce it? And in case of heterocycles, if you have E stands for ester here, right. If you have bromine, you can straightaway use zinc, actually straightaway zinc and with an additive lithium chloride. Apparently this reaction is pretty friendly reactions. You can straightaway produce the corresponding zinc compounds. Okay. So, take any other 5-member heterocycle within thiazole, for example, bromine, now 2 bromines, now zinc would be organozinc would be produced. Again, now in this case the options, right. The bromine, there are 2 different kinds of bromine, the one that is more labile, and we know which one is more labile because the one between the 2 heteroatoms, and so zinc is placed here and the rest of the things, and then reactivity wise is quite similar, and then also there are reactions actually by which one can do the zincation by direct deprotonations. For example, in this case it is a 5-member ring, sorry, pyrazole derivative, oxapyrazole derivative, and pyridine here, hydrogen here. So, you want to do the deprotonation here, that means you have to stop the nucleophilic addition. So, what you do is, this is a recent reagent TMP, all of us know what is tetramethyl pipyridite 2 and then zinc, and then all kinds of the recipes, 2 magnesium, this is actually a Nockel's reagent, magnesium chloride, and what else, one more additive is there, lithium chloride. So, I mean anybody can guess now. Actually lithium chloride has a remarkable ability. I do not know, I am unable to actually find the real literature, original literature, but people say lithium chloride has a lot of advantages, lot of important reactivity profiles. We have to dig out that. If anybody you can just take special interest in lithium chloride is a very useful additives in organic chemistry. Any case, so then you got this obviously zincation done, right. So, zincation done, and then this zincation, and there are reactions, all possible reactions one can do it. One of these reactions, I think I will just write, this is something probably you do not know. This is a reagent, in fact this is a reagent we made in our lab, very interestingly. We actually make it from diphenyl disulfide, and also you remember, if you do this oxidation with metachloroperbenzoic acid, one particular sulfur get oxidized first. See, once if the corresponding reagent is this, if you try to oxidize this, this gets oxidized. Okay, that means first oxidation is S, SO, and this. Second oxidation one would expect on this here, but that does not go. the same sulfur undergoes oxidation. Give an explanation next class maybe. Okay. And so possible, but nowhere I have found the I mean, we can suspect all this, we can explain all these things, yes, that is could be one of the reasons, that could be one of the reasons, but nobody has courage to write that in black and white. Writing in black and white means you need to have extra courage. Okay. You should be free from criticism, critics and all these things. Any case, what next then? The product should be an addition of an electrophile, right. So, addition of an electrophile, and this is phenyl. So, phenyl and what is it? What is the electrophile? SO. What is the electrophile? That is what everybody would think. Again, that is the reason I have chosen this example. Okay. In all these carbon ion chemistry, if you want an SPH, actually we did that in our lab. Okay. And so, and then also I think we will talk about the rest of the things about the organogen compounds in the next class, because all of us know Negishi coupling, etc. I think one of I have learned a little bit of these or more of it. And then lastly, this is this last example. I think maybe in the next class we talk about this a little and then this. From the name you can make out the nationality of the person, right. Bartoli from where? Bartoli from very good, Italy, right. Some of the names are typical, right. Shiva, Narasimha, all these are Japanese. So, similarly, this is Bartoli is from Italy, yes, Italian scientist. This morning I was asking some of you, have you ever come across a brand new organic reactions in recently, which was not reported, or any similar version of this not reported? This is one of the reactions which is pretty a brand new reaction. Reason being, it is a reaction with a Grignard reagent, and this starting material is an old one, nitrobenzene has been known in the literature for so many years. Grignard also has been known for, right. Grignard also has been known in the literature for so many years. So, you can just write magnesium bromide, and in this example, particular example, actually ortho substituted nitro compound is taken, and the temperature of the reaction is minus 40 degree. So, what do you expect? Let us say if Bartoli did not do the reaction, what would you have expected? Okay, this R1, had it been X and all these things, then that addition substitution reaction would have taken place, but that is not there. So, it is a, let us say carbon substituent. This is a carbon substituent, this is a carbon substituent, and the name implies the reaction result is an indole derivative. So, that is really a brand new reactions, and what you get is this indole reactions. So, and well defined means, sorry, this is 2, this is 2 and this is 3. So, well defined reactions, it's nice, region specific, single product. Only disadvantage you have to take note of this. This is required in high. So, 2 of the molecules of the Grignard, 2 of the molecules are destroyed during the process. Okay. This is a pretty very good reaction, and some quite a few people are using this or making these indole derivatives. So, maybe in the next class we will talk about the mechanism of this reaction. In brief, that one is used up for the framework, the construction of the frame, and the 2 other Grignards are spoiled or were consumed, one for the reductions of the nitro to the nitroso compound, and secondly other one equivalent is consumed to deprotonations of one of these hydrogen. So, eventually all of them are required, that means that is the requirement, minimum 3 equivalents of this thing. Okay. And so, we meet again on next Friday at 9:30. So most of you know, right, this cross coupling etc. Maybe we will just very quickly review and then we will stop there.